Good day all. In this video, we will discuss about what is a signal and what is a system and the various types of signals and systems. So what is a signal? A signal is defined as any physical quantity that varies with time, space, or any other independent variable. So in our real world, we come across lot of signals. So a signal is a pattern of variation that carry information. And the signals are represented mathematically as a function of one or more independent variables. And a picture is a brightness as a function of two spatial variables, x and y. We represent the picture as x and y. A signal may be a real valued or scalar valued function of an independent variable t. So normally a signal is represented as a function of time, that is t. Let us look at some of the examples of signals. Electrical signal, acoustic signal, video signal, biological signal, and noise is also a signal. So if we take an electrical signal, so the signal that is passing over this voltage and current that is passing over this circuit, electrical circuit, we call it as an electrical signal. And acoustic signal is nothing but audio or speech signal. We can also tell that as analog or digital signal. And video signal represents our video. That is nothing but video signal. So the video signal signifies the intensity variations that occur in an image with respect to time. And next one is biological signals. It is nothing but sequences of bases in a gene. So those are some of the biological signals that are generated in a sequence. And noise is also an unwanted signal, but that is also present. That is also one type of signal. So these are some of the signals. And we in real world, there are a lot of types of signals are there. We come across, for example, electromagnetic signal. Different types of signals are present. So this is an example for how do we measure the signal. So here, if we look at this signal, so here in this x-axis is always with reference to time. This x-axis is always with reference to time, and y-axis is with reference to amplitude. Always y-axis is with reference to amplitude. And here, depending upon the time period, this amplitude, what is the variation of amplitude in the signal is measured here. It is plotted here. You look at, so this is one cycle of a sinusoidal waveform. So, and also we call this one cycle as one period. So here in this graph, it is denoted from this region to this region. So one cycle, one positive half cycle and one negative half cycle together will form one cycle that we call it as one time period. This is how we measure the signals. Now we will look at some of the signal basics. That is continuous time. Signals can be classified as continuous time and discrete time signals. So here continuous time signals are real world signals. That is, it take on real or complex values as a function of an independent variable that ranges over real numbers and are denoted by x of t. And discrete time signals take on real or complex values as a function of an independent variable that ranges over integer values and are denoted by x of n. So the difference between this continuous time and discrete time is continuous time exists at all values of t, whereas discrete time signal exists only at integer values of n. Only a discrete instance of time. This is what you need to remember. The discrete time signal exists only at discrete instance of time. So here as it is marked here, so 0, here it is 1, here it is 2, here it is 3, n is equivalent to, this is n axis. This is n axis. This is n axis. So here this n axis, n is equivalent to 1, n is equivalent to 2, n is equivalent to 3 and so on. And similarly in the negative side also. Whereas continuous time here, it is with respect to t. This axis is with respect to t. That is the time axis. So here, if we look at the signal, for all instance of time, the signal has some value. That is called as a continuous time signal. Here, this x of n is a discrete time signal because it exists only at discrete instance of time. So this you need to remember very well. Some of the analog signals we have in real time. So first one is the human voice is the best example of the analog signal. So here if we look at the ear recognizes sounds of 20 kilohertz or less. And the AM amplitude modulation radio, AM radio has the frequency range of this 535 kilohertz to 1605 kilohertz. Similarly, FM radio has the frequency range from 88 megahertz to 108 megahertz. So this is how the signal, the time duration, the time from the transmitter to receiver, how it is measured is given here. And here the thermometer, how the heat is measured. And here how the signal is transmitted. That is, the signal is transmitted from this photograph, how it is captured. So that is in the camera, how the signal is captured. So that is shown here. The next one is digital signals. So here digital signals, it is represented by a square wave, either 0 or 1, high or low, only 2 states. So all data are represented by binary values. So a single binary digit, we call it as a bit. So here the transmission of continuous group of bits, we call it as a bit stream. And not all decimal values can be represented by binary. So this kind of signal is called as a digital signal. It has only 2 states, high or low, 0 or 1. Now we will come to the main part of classification of signals. So signals are classified as deterministic and random signal, even and odd signal, periodic and aperiodic signal, energy and power signals. So now we will discuss one after the other. So first one is deterministic signal. So what is a deterministic signal? A signal that can be determined at all instants of time correctly. That is called as a deterministic signal. So the behavior of these signals is predictable with respect to time. And there is no uncertainty with respect to its value at any time. And these signals can be expressed very correctly by mathematical function. So that is called as a deterministic signal. So here our deterministic signal example taken is sine 3t. So it is a deterministic signal. So the opposite of the deterministic signal is non-deterministic or random signals. So behavior of these signals is random. We cannot predict the nature of the signal. So that is why we call it as a random signal. And there is always an uncertainty with respect to its value at any time. And these signals can't be expressed mathematically, only by a statistical function. We can represent, we can analyze or predict how the signal is occurring. And the example of this non-deterministic signal is thermal noise. Okay, so thermal noise is non-deterministic in nature, and that is random in nature. So these are the two types, that is deterministic and random signals. So next important type of signal is even and odd signals. This is nothing but a signal is even if we say that a signal x of t or g of t, which is equivalent to g of minus t. That is the negative part and the positive part, that is in the full axis from minus infinity to infinity. The negative part is equivalent to the positive part. That is, the amplitude of the negative part is equivalent to the amplitude of the positive part. So that is called as an even function. The reverse, that is, if it is minus of g of minus t or x of t is equivalent to minus of x of minus t, that is called as an odd function. So the example, correct example of an even function is the cosine. Cosine function is an even function, whereas sinusoidal function is an odd function. So now given a signal g of t, so we can calculate the even and odd part of the function. So the even part of the function g of t is equivalent to g of t plus g of minus t by 2. Whereas the odd part of the function g naught of t is equivalent to g of t minus g of minus t by 2. So by these two equations, whatever signal given, that is any signal given g of t or x of t, whatever signal is given, we can find out the even and odd part of the signal. So a function whose even part is 0 is odd, and a function whose odd part is 0 is even. So this is an important point we need to note down. Similar manner, in discrete time, even and odd signals. So there the t is represented as n here. So g of n is equivalent to g of minus n is the even function, and g of n is equivalent to minus g of minus n is the odd function. Similarly, the even component and odd component are found by these equations. Now coming to the next signal, that is periodic and non-periodic signals. So what is a periodic signal? A signal is periodic if it repeats after the same time, that is the fundamental time period t. So here we have represented as t naught. So the t naught is nothing but the fundamental time period. T naught is the fundamental time period. T naught is the fundamental time period. So given a signal x of t, x of t is a continuous time signal. So this x of t is periodic if and only if x of t is equivalent to x of t plus capital T naught, where T naught is the fundamental time period for any t and any integer n. So here we'll discuss this example. X of t is equivalent to a cos omega t. So if it has to be periodic, it has to satisfy the condition x of t is equivalent to x of t plus capital T naught or t. This is the condition for a periodic signal. So here we had put x of t plus t naught is equivalent to a cos omega t plus t naught. In the place of t, we had put t plus t naught in the function a cos omega t. So now we had expanded a cos omega t plus omega t naught. We had expanded. So when this equation, that is a cos omega t and a cos omega t plus omega t naught will be equal only when this omega t naught is equivalent to 2 pi. Only when this omega t naught is equivalent to 2 pi. Why it is like that? So here cos omega theta, that is cos 2 pi plus theta is equivalent to cos theta. So this is the identity that we all know. So cos 2 pi plus theta is equivalent to cos theta. So based on this, here if we put this omega t naught is equivalent to 2 pi, here we get this equation will become cos omega t. So from that we have derived this formula, the formula in the third step. That is, so T naught is equivalent to what? 2 pi by omega. So T naught is equivalent to 2 pi by omega. Okay, and T naught is also equivalent to 1 by F naught. So here, this omega is nothing but 2 pi F naught. Omega, you know, that is the angular frequency, which is equivalent to 2 pi F naught. So here, from that, we can find the equation. This is the equation for T naught. Okay, T naught is equivalent to 1 by F naught, or T naught is equivalent to 2 pi by omega. So now coming to this non-periodic signals. So here, this non-periodic signal is nothing but a signal which does not satisfy the condition x of t is equivalent to x of t naught t plus t naught is called as a non-periodic signal. A non-periodic signal is assumed to have a period t is equivalent to infinity. And the example of this non-periodic signal is an exponential signal. So the important condition of periodicity for a discrete time signal. So for a discrete time signal, it is quite different. So here in the discrete time, one point what we have to notice, the signal occurs only at discrete instance of time. So the time period should also be discrete, that is an integer value. So what we do, we will find out the 2 pi by omega naught and we will multiply this n will be equivalent to 2 pi by omega naught and we will multiply with some constant value k. So this constant value k will take some value, some integer value to make this n to be the smallest possible integer. So for satisfying the above condition, the frequency of the discrete time signal should be ratio of two integers. Okay, so this is the equation for the discrete time signal. So sum of periodic signals, how do we find out? So initially in the previous slides we discussed if a signal is given, how to find out the period. And if a discrete time signal is given, how to find out the time period. So if two signals are added together, how do we find out the time period? That is fundamental time period T naught. So suppose x of t is equivalent to x1 of t plus x2 of t is given. So if it has to be periodic, then x of t must be added as x of t plus capital T. So x of t plus capital T is equivalent to x1 of t plus m1 t1 plus x2 of t plus m2 t2. We take some value m1 m2. So now we need to find out the fundamental time period. So how do we find out? M1 T1 is equivalent to some constant. M2 T2 is equivalent to T naught. So here this T1 by T naught, T1 by T2 should be ratio of integers. Should be ratio of integers or rational numbers. Ratio of integers. Ratio of integers are rational numbers. So when we take this example, cos t pi by 3 plus sin t pi by 4. So here t1 is equivalent to 2 pi by 3 and t2 is which works out to 6. T2 is equivalent to the second angular frequency. That is this if we take it as omega 1. This we can take it as omega 1. This we can take it as omega 2. So here the second angular frequency T2 is equivalent to 2 pi by 4. So that works out to 8. So now T1 by T2 is equivalent to 6 by 8, which is equivalent to 3 by 4, which is a rational number. So which we can take it as M2 by M1. So here that is equivalent to. So if you just multiply this, if you cross multiply, if we get, see here, T1 by T2 is equivalent to 6 by 8 or 3 by 4. Just cross multiply this. So if we cross multiply, we get 4T1 is equivalent to 3T2, which is equivalent to what? Some T naught. So here T1 value, what we had got? T1 value is 6. And T2 value is what? 8. So if we substitute, we get 24. This is our T naught. This is how we find out the fundamental time period T naught for any periodic signal, that is sum of two periodic signals. Hope you had understood. So sum of periodic signals may not always be periodic. So here the same way we had found out, this is the second example. So T1, T2 we had found out. And here T1 by T2 is square root of 2, which is an irrational number. It is not a ratio of two integers. So we say that it is a aperiodic signal. So now we'll move on to the next type of signal, that is energy and power signal. So what is an energy signal? A signal with finite energy and zero power is called as an energy signal. That is represented as energy E is from between 0 to infinity. That is finite energy, some finite number. and power is also equivalent to 0. So the total energy of a signal is defined as the area under the square of the magnitude of the signal, which is given by, given a signal x of t, for any given signal x of t, the energy, total energy of the signal is given by integral minus infinity to infinity mod x of t, the whole square dt. We can also write the total energy as limit t tends to infinity integral minus t to t mod x of t, the whole square dt. And normally the energy is measured in joules. The energy is measured in joules. Then next is the power signal. So some signals have infinite signal energy. In that case, it is more convenient to deal with the average signal power. So the power must be finite and energy is infinity. In that case, that is a power signal. So the average power of the signal is given by limit t tends to infinity 1 by t integral minus t by 2 to t by 2 mod x of t the whole square dt, or the same equation we can write it as p is equivalent to limit t tends to infinity 1 by 2t 1 by 2t integral minus t to t mod x of t the whole square dt, mod x of t the whole square dt, and the power is measured in watts. Normally the power is measured in watts, and the RMS value of the signal, any given signal x of t, RMS value of any given signal x of t is given by square root of power. RMS value of any given signal x of t is given by square root of power. So the energy and power for a discrete time signal, the definition is the same. The equation alone differs. For a discrete time signal x of n, E is equivalent to summation n is equivalent to minus infinity to infinity mod x of n the whole square. This can also be represented as limit n tends to infinity summation n is equivalent to minus n to n mod x of n the whole square joules. Similarly, in discrete time signal, the power equation is given by limit n tends to infinity 1 by 2n summation n is equivalent to small n is equivalent to minus capital N to n minus 1 mod x of n the whole square, or I can also write it as power is equivalent to limit n tends to infinity 1 by 2n plus 1 summation n is equivalent to minus n to n mod x of n the whole square. So this is the equation for power in discrete time signal. So till now we discussed about what is a signal, what are different types of signals, that is deterministic and random signal, periodic and aperiodic signal, even an odd signal, energy and power signal. So now we'll move on to the next half of this lecture, that is system. So what is a system? So every signal is to be given to a system. So without a system, the signal will not work. We do not know what the signal will do. So the system is one which processes the input signals to produce some output. So whatever input signal we give to a system, relevant to that and what system we are giving. So based on that, you get the output signal. So a system is a combination of element that manipulates one or more signals to accomplish a function and produces some output. So that is a system. So here, if you give an input signal, that is continuous time input signal, you get a continuous time output signal. If we give a discrete time input signal, we get a discrete time output signal. So these are some of the examples of systems. Some of the examples. There are many types of systems available in the real world. This is some of the examples. This electric circuit is also a system. There is a circuit involving a capacitor can be viewed as a system that transforms the source voltage signal to a voltage across the capacitor. So that is an electric circuit system. The next one is a communication system. We all experience, we all do communication, we all have mobile phones with us. So the communication is going on all the time with our mobile phones. So the basic of communication is the transmitter. Basic blocks is the transmitter, channel, and receiver. So these are the three subsystems the communication system has. So the signal has to be transmitted from one end. The channel is a system which processes the transmitted signal. Then at the receiver end, the signal is received and it is processed and it is in the viewable form, whether it is audio or video, whatever it is. So in that form, it is converted. So the channel typically what it does, it attenuates and adds noise to the transmitted signal. So that has to be processed by the receiver end. So the receiver end, the function is, the signal complexity is very high at the receiver end. The signal, it has to be processed, it has to remove the noise, and the actual signal that is sent after modulation from the transmitter has to be demodulated, decoded, and it is to be given at the receiver end. And the next system is a biomedical system. So it is used for biomedical signal processing. And another one is control system. This is a generic term they had given. So there are different types, hydraulic, pneumatic, different types of control systems are available. So some of the examples of system we will discuss now. So consider a RL series circuit. So here there is a voltage and then there is a resistor and an inductor. So the voltage across the resistor is denoted by VR. And the voltage across the inductor is denoted by VL of T. And with respect to time, that is the time and the current flow. Normally, the current flow we will measure. The current flow I only we will measure. That is with respect to time. So the VL of T, that is the voltage VL of T across the inductor is given by L into di of T by dt. And VR is denoted by I of T into R. So the total voltage across this circuit is given by VR plus VL of T, which is equivalent to I of T into R plus L into di of T by dt. So here when we look at this equation, this is a first order equation. Here, this D is only differentiated once. Based on the differentiation level, we say that as first order, second order, like that. So order of the system. So what is the order of the system? Order of a continuous time system is the highest power of the derivative. That is a differentiation associated with the output in the differential equation. This kind of equation, we call it as a differential equation. That is in continuous time, we represent the system by a differential equation, whereas in discrete time, we represent the system as a difference equation. So for example, the order of the system shown is 1, as it is only differentiated once. So here the order of the system for a discrete time system, as I had told you, this discrete time system is represented by a difference equation. That is difference from this equation itself. It is represented by difference by which the output is delayed. So here the order of the system is 1. That is the highest number in the difference equation by which the output is delayed. That is the order of the system in the difference equation. So now we will classify the systems as static and dynamic, causal and non-causal, linear and non-linear, time variant and time invariant, stable and unstable, invertible and non-invertible systems, or inverse systems. So first type of system is static and dynamic system. So static and dynamic system is memoryless or with memory system. So a static system is a memoryless system. That is, it doesn't have any storage devices. That is, the output signal depends on the present value of the input signal. So for example, if I of t is equivalent to 1 by r into v of t, that is a static signal because here the output at time t depends on the input at time t. If we put t is equivalent to 0, here here also v is equivalent to 0. At the same time only it depends. So this is called as a memoryless system. Whereas a dynamic system has memory. That is, it depends on past values and future values of the input signal. It has storage device. I of t is equivalent to 1 by L integral minus infinity to t v of tau d tau. And this equation is y of n is equivalent to x of n plus x of n minus 1. So if we substitute, if we have a doubt, if we substitute this n is equivalent to 0, for n is equivalent to 0, if we substitute y of 0 is equivalent to x of 0 plus x of minus 1. So this output at n is equivalent to 0 depends on input at n is equivalent to 0 and input at n is equivalent to minus 1. So it depends on the past values also. So that is why this is called as a dynamic system. So the dynamic system is one which possesses memory. So here is another example of a static or dynamic system. So here, if we look at this system, here there is a voltage source, then resistor, and there is a capacitor. So we all know the nature of the capacitor. The capacitor is a memory device which stores charge, because of which voltage across it can't change immediately. So that is a capacitor. So here, but resistor is a memoryless device, whereas capacitor has memory. So this system is called as a dynamic system. Causal and non-causal system. So the causal system is one which depends on the present and the past values, not on future values. So that is a causal system. So y of n is equivalent to x of n plus 1 by 2 into x of n minus 1. So that is a causal system. So here the system depends on the present as well as past values, not on the future values. Next one is anti-causal system. A system is said to be anti-causal if the present value of the output signal depends only on the future values of the input signal. The next type of system is linear and non-linear system. A system is said to be linear if it satisfies the principle of superposition. So what is the superposition principle? If the weighted sum of input is given to the system, the output should be weighted sum of outputs. So that is the superposition principle. So for checking the linearity of a given system, firstly, we check the response due to linear combination of inputs. So then we combine the two outputs linearly in the same manner as the inputs are combined, and again total response is checked. So if the response in step 2 and 3 are the same, the system is linear, otherwise system is non-linear. So this is linear and non-linear based on superposition principle. The next one is time invariant and time variant system. A system is said to be time invariant if the time delay or time advance of the input signal leads to identical time shift in the output signal. So if we delay the input by some t, the output should also be delayed by the same t. Next system is stable and unstable system. A system is said to be stable if you give a bounded input to the system, it should generate a bounded output. It means that if there is some finite input is given to the system, the output should be finite. So that is called as a stable system. Otherwise, it is unstable. So that is why we call it as this stability criterion, we call it as a Bibo stability criterion. So this is another one example for this stable and unstable systems. So if for n value, if you give a stable input, it should generate a stable output for all value of n. So the system represented by this is unstable as if a is greater than 1. So let us assume a x of t is equivalent to u of t. Then At every instant, u of t, it will keep on multiplying with a, and this u of t is not bounded. It goes till infinity, so it is unstable. The next system is invertible and non-invertible system or inverse system. That is, if a system is said to be invertible, it has an inverse system. That is, the x of t is given to a system, you get an output y of t. If y of t is given to the inverse of the system, it has to generate x of t. That is called as an invertible system. Otherwise, it is non-invertible system. Thank you.